Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on three-phase three-wire AC systems. By solving these problems, we shall learn how to determine the neutral shift voltage applying Millman's theorem for a star-connected unbalanced load fed from a symmetrical three-phase three-wire AC source. We shall also learn how to compute load voltages and line currents using this value of neutral shift voltage. For a three-phase three-wire symmetrical AC source with phase sequence ABC, taking phase voltage VA as reference, we can write phase voltage VA equals to V phase at an angle 0 degree, VB equals to V phase at an angle minus 120 degree, and VC equals to V phase at an angle plus 120 degree. Here supply voltage per phase V phase equals to VL by root 3, where VL is the magnitude of line-to-line supply voltage. Applying Kirchhoff's voltage law, we get expressions for per phase load voltages VAN dash equals to VA minus VN dash N, VBN dash equals to VB minus VN dash N, and VCN dash equals to VC minus VN dash N. Here VN dash N is the neutral shift voltage. Line currents IA equals to VAN dash divided by ZA, or VA minus VN dash N into YA. IB equals to VBN dash divided by ZB, or VB minus VN dash N into YB. And IC equals to VCN dash divided by ZC, or VC minus VN dash N into YC. Here YA, YB and YC are the per phase load admittances. Applying Kirchhoff's current law to load start point N dash, we get IA plus IB plus IC equals to 0. Using expressions for currents, we get VA minus VN dash N into YA plus VB minus VN dash N into YB plus VC minus VN dash N into YC equals to 0. From this equation, we get expression for neutral shift voltage VN dash N equals to VA into YA plus VB into YB plus VC into YC divided by YA plus YB plus YC. Let us put X equals to VA into YA plus VB into YB plus VC into YC, and equivalent admittance YEQ equals to YA plus YB plus YC. Therefore, VN dash N equals to X divided by YEQ. A star-connected unbalanced load has following admittances: YA equals to 0.25 mho, YB equals to 0.125 mho, and YC equals to 0.05 mho respectively. We have to determine the neutral shift voltage and the line currents, assuming a system line-to-line voltage of 240 volts and phase sequence ABC. Let us first write down the given data. Line-to-line supply voltage VL equals to 240 volts. For a star-connected load, supply voltage per phase V phase equals to VL by root 3, that is equal to 240 divided by root 3, that gives us 138.564 volt. Taking A phase voltage VA as reference, for phase sequence ABC, we can write phase voltage VA equals to V phase at an angle 0 degree, that is equal to 138.564 volt at an angle 0 degree. In Cartesian form, this may be written as 138.564 plus J times 0 volt. VB equals to V phase at an angle minus 120 degree, that is equal to 138.564 volt at an angle minus 120 degree. In Cartesian form, this may be written as minus 69.282 minus J times 120 volt, and VC equals to V phase at an angle plus 120 degree, that is equal to 138.564 volt at an angle plus 120 degree. In Cartesian form, this may be written as minus 69.282 plus J times 120 volt. Given per phase load admittances YA equals to 0.25 mho, YB equals to 0.125 mho, and YC equals to 0.05 mho. Let us now determine X equals to VA into YA plus VB into YB plus VC into YC. Using values we get X equals to 22.5167 minus J times 9 volt mho. In polar form, this may be written as 24.248748 volt mho at an angle minus 21.7868 degree. Now we shall calculate equivalent admittance. YEQ equals to YA plus YB plus YC. Using values we get 0.425 mho. Now we shall calculate neutral shift voltage. Vn dash n equals to X divided by YEQ. Using values we get 24.248748 at an angle minus 21.7868 degree divided by 0.425. That gives us 57.0559 volt at an angle minus 21.7868 degree. Expression for voltage drop across each load impedance Van dash equals to Va minus Vn dash n, Vbn dash equals to Vb minus Vn dash n, and Vcn dash equals to Vc minus Vn dash n. We have determined neutral shift voltage Vn dash n equals to 57.0559 volt at an angle minus 21.7868 degree. This may be written in Cartesian form as 52.9805 minus J times 21.1765 volt. Using values we get Van dash equals to 85.5835 plus J times 21.1765 volt. In polar form, this may be written as 88.1645 volt at an angle plus 13.898 degree. Vbn dash equals to minus 122.2625 minus J times 98.8235 volt. In polar form, this may be written as 157.2075 volt at an angle minus 141.052 degree, and Vcn dash equals to minus 122.2625 plus J times 141.1765 volt. In polar form, this may be written as 186.759 volt at an angle plus 130.8934 degree. For a star-connected load, line currents are equal to phase currents. Expressions for line currents IA equals to VAN dash into YA, IB equals to VBN dash into YB, and IC equals to VCN dash into YC. We have obtained voltage drop across each load impedance VAN dash equals to 88.1645 volt at an angle plus 13.898 degree. VBN dash equals to 157.2075 volt at an angle minus 141.052 degree, and VCN dash equals to 186.759 volt at an angle plus 130.8934 degree. Using values we get IA equals to 88.1645 at an angle plus 13.898 degree into 0.25, that gives us 22.0411 ampere at an angle plus 13.898 degree. IB equals to 157.2075 at an angle minus 141.052 degree into 0.125, that gives us 19.651 ampere at an angle minus 141.052 degree, and IC equals to 186.759 at an angle plus 130.8934 degree into 0.05, that gives us 9.33795 ampere at an angle plus 130.8934 degree. An unbalanced 3-wire star-connected load is connected to a symmetrical supply of 415 volts. If the load impedances are ZR equals to 7 ohm at an angle 30 degree, ZY equals to 9 ohm at an angle 60 degree, and ZB equals to 8 ohm at an angle 45 degree, we have to determine the neutral shift voltage, line currents, and load voltages. Let us first write down the given data. Per phase load impedances ZR equals to 7 ohm at an angle 30 degree, ZY equals to 9 ohm at an angle 60 degree, and ZB equals to 8 ohm at an angle 45 degree. Let us now calculate per phase load admittances. YR equals to 1 upon ZR, that is equal to 1 upon 7 at an angle 30 degree. That gives us 0.14286 mho at an angle minus 30 degree. In Cartesian form, this may be written as 0.12372 minus J times 0.07143 mho. YY equals to 1 upon ZY, that is equal to 1 upon 9 at an angle 60 degree. That gives us 0.11111 mho at an angle minus 60 degree. In Cartesian form, this may be written as 0.05556 minus J times 0.0962 mho. And YB equals to 1 upon ZB, that is equal to 1 upon 8 at an angle 45 degree. That gives us 0.125 mho at an angle minus 45 degree. In Cartesian form, this may be expressed as 0.0884 minus J times 0.0884 mho. Now we shall determine equivalent admittance. YEQ equals to YR plus YY plus YB. Using values we get 0.26768 minus j times 0.25603 more. In polar form, this may be written as 0.3704 more at an angle minus 43.726 degree. Given line-to-line supply voltage VL equals to 415 volts. When a star-connected load is supplied by a symmetrical three-phase AC source, supply voltage per phase V phase equals to VL by root 3, that is equal to 415 divided by root 3, that gives us 239.6 volt. Taking R phase voltage VR as reference, for phase sequence RYB we can write phase voltage VR equals to V phase at an angle 0 degree, that is equal to 239.6 volt at an angle 0 degree. In Cartesian form, this may be written as 239.6 plus j times 0 volt. Vy equals to V phase at an angle minus 120 degree, that is equal to 239.6 volt at an angle minus 120 degree. In Cartesian form, this may be written as minus 119.8 minus j times 207.5 volt, and Vb equals to V phase at an angle plus 120 degree, that is equal to 239.6 volt at an angle plus 120 degree. In Cartesian form, this may be written as minus 119.8 plus j times 207.5 volt. Let us now calculate x equals to VR into YR plus Vy into YY plus Vb into YB. We have obtained per phase load admittances YR equals to 0.14286 more at an angle minus 30 degree, YY equals to 0.11111 more at an angle minus 60 degree, and YB equals to 0.125 more at an angle minus 45 degree. Using values we get x equals to 10.77304 plus j times 11.81485 volt more. In polar form, this may be written as 15.989 volt more at an angle plus 47.6408 degree. Expression for neutral shift voltage Vn' equals to x divided by Yeq. We have determined equivalent admittance Yeq equals to 0.3704 more at an angle minus 43.726 degree. Using values we get Vn' equals to 15.989 at an angle plus 47.6408 degree divided by 0.3704 at an angle minus 43.726 degree, that gives us 43.1668 volt at an angle plus 91.3668 degree. Expression for per phase load voltages Vrn' equals to Vr minus Vn', Vyn' equals to Vy minus Vn', and Vbn' equals to Vb minus Vn'. We have obtained neutral shift voltage Vn' equals to 43.1668 volt at an angle plus 91.3668 degree. In Cartesian form, this may be written as minus 1.0297 plus J times 43.1545 volt. Using values we get Vrn dash equals to 240.6297 minus J times 43.1545 volt. In polar form, this may be written as 244.47 volt at an angle minus 10.1673 degree. Vyn dash equals to minus 118.7703 minus J times 250.6545 volt. In polar form, this may be written as 277.37 volt at an angle minus 115.3535 degree, and Vbn dash equals to minus 118.7703 plus J times 164.3455 volt. In polar form, this may be written as 202.77 volt at an angle plus 125.8551 degree. Expressions for line currents: IR equals to Vrn dash into YR, IY equals to Vyn dash into YY, and IB equals to Vbn dash into YB. We have determined per phase load voltages. Vrn dash equals to 244.47 volt at an angle minus 10.1673 degree. Vyn dash equals to 277.37 volt at an angle minus 115.3535 degree, and Vbn dash equals to 202.77 volt at an angle plus 125.8551 degree. Using values we get IR equals to 244.47 at an angle minus 10.1673 degree into 0.14286 at an angle minus 30 degree, that gives us 34.925 ampere at an angle minus 40.1673 degree. IY equals to 277.37 at an angle minus 115.3535 degree into 0.11111 at an angle minus 60 degree. That gives us 30.8186 ampere at an angle minus 175.3535 degree. And IB equals to 202.77 at an angle plus 125.8551 degree into 0.125 at an angle minus 45 degree, that gives us 25.3463 ampere at an angle plus 80.8551 degree. In the circuit shown, we have to determine the line currents and load voltages. The load is supplied by a symmetrical 208 volt AC supply with phase sequence ABC. We have to select the line voltage VAB as reference. Let us first write down the given data. Per phase load impedances ZA equals to R equals to 5 ohm. In polar form, this may be written as 5 ohm at an angle 0 degree. ZB equals to RL plus J times XL, that is equal to 3 plus J times 4 ohm. In polar form, this may be written as 5 ohm at an angle 53.13 degree. And ZC equals to RC minus J times XC, that is equal to 6 minus J times 8 ohm. In polar form, this may be written as 10 ohm at an angle minus 53.13 degree. Now we shall determine per phase load admittances. Ya equals to 1 upon Za, that is equal to 1 upon 5 at an angle 0 degree. That gives us 0.2 mho at an angle 0 degree. In Cartesian form, this may be expressed as 0.2 minus J times 0 mho. Yb equals to 1 upon Zb, that is equal to 1 upon 5 at an angle 53.13 degree. That gives us 0.2 mho at an angle minus 53.13 degree. In Cartesian form, this may be written as 0.12 minus J times 0.16 mho, and Yc equals to 1 upon Zc, that is equal to 1 upon 10 at an angle minus 53.13 degree. That gives us 0.1 mho at an angle 53.13 degree. In Cartesian form, this may be written as 0.06 plus J times 0.08 mho. Now we shall calculate equivalent admittance. Yeq equals to Ya plus Yb plus Yc. Using values we get 0.38 minus J times 0.08 mho. In polar form, this may be expressed as 0.388333 mho at an angle minus 11.88866 degree. Given line-to-line supply voltage VL equals to 208 volts when a star-connected load is supplied by a symmetrical 3-phase 3-wire AC supply voltage per phase V phase equals to VL by root 3, that is equal to 208 divided by root 3, that gives us 120 volts. Taking the line voltage VAB as reference for phase sequence ABC, we can write phase voltage VA equals to V phase at an angle minus 30 degree, that is equal to 120 volts at an angle minus 30 degree. In Cartesian form, this may be written as 103.923 minus J times 60 volt. VB equals to V phase at an angle minus 150 degree, that is equal to 120 volts at an angle minus 150 degree. In Cartesian form, this may be expressed as minus 103.923 minus J times 60 volt, and Vc equals to V phase at an angle plus 90 degree, that is equal to 120 volts at an angle plus 90 degree. In Cartesian form, this may be written as 0 plus J times 120 volts. Now we shall calculate X equals to VA into Ya plus VB into Yb plus Vc into Yc. We have determined per phase load admittances. Ya equals to 0.2 mho at an angle 0 degree, Yb equals to 0.2 mho at an angle minus 53.13 degree, and Yc equals to 0.1 mho at an angle 53.13 degree. Using values we get X equals to minus 10.88616 plus J times 4.62767 volt mho. In polar form, this may be written as 11.82894 volt mho at an angle plus 156.9698 degree. Expression for neutral displacement voltage Vn dash n equals to X divided by Yeq. we have obtained equivalent admittance YEQ equals to 0.38833 mho at an angle minus 11.88866 degree. Using values we get Vn dash n equals to 11.82894 at an angle plus 156.9698 degree divided by 0.38833 at an angle minus 11.88866 degree. That gives us 30.461 volt at an angle plus 168.85846 degree. Expression for per phase load voltages VAN dash equals to VA minus VN dash N, VBN dash equals to VB minus VN dash N, and VCN dash equals to VC minus VN dash N. We have determined neutral displacement voltage Vn dash n equals to 30.461 volt at an angle plus 168.85846 degree. In Cartesian form, this may be written as minus 29.8869 plus j times 5.8861 volt. Using values we get VAN dash equals to 133.8099 minus j times 65.8861 volt. In polar form, this may be written as 149.15 volt at an angle minus 26.215 degree. VBN dash equals to minus 74.0361 minus j times 65.8861 volt. In polar form, this may be written as 99.11 volt at an angle minus 138.33 degree, and VCN dash equals to 29.8869 plus j times 114.1139 volt. In polar form, this may be written as 117.963 volt at an angle plus 75.3236 degree. Expression for line currents IA equals to VAN dash into YA, IB equals to VBN dash into YB, and IC equals to VCN dash into YC. We have determined per phase load voltages VAN dash equals to 149.15 volt at an angle minus 26.215 degree, VBN dash equals to 99.11 volt at an angle minus 138.33 degree, and VCN dash equals to 117.963 volt at an angle plus 75.3236 degree. Using values we get IA equals to 149.15 at an angle minus 26.215 degree into 0.2 at an angle 0 degree. That gives us 29.83 ampere at an angle minus 26.215 degree. IB equals to 99.11 at an angle minus 138.33 degree into 0.2 at an angle minus 53.13 degree. That gives us 19.822 ampere at an angle minus 191.46 degree, and IC equals to 117.963 at an angle plus 75.3236 degree into 0.1 at an angle 53.13 degree. That gives us 11.7963 ampere at an angle plus 128.4536 degree. So today we have solved a couple of numerical problems on three-phase three-wire AC systems. By solving these problems, we have learned how to determine the neutral shift voltage for a star-connected unbalanced load supplied from a symmetrical three-phase three-wire AC source applying Millman's theorem. We have also learned how to compute load voltages and line currents using this value of neutral shift voltage. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.